here's a problem for class 5, an example problem. I'm adding this kind of at the last minute. I noticed that a previous example was too much like the homework problem, and I kind of wanted to replace it for a while anyway. So this is an excerpt from my book, The Engineering Dynamics Course Companion. We have a race car that's traveling from point A and to point B along this curved section is a 100-yard radius right here. The 2 points are 150 degrees apart, so it'll be like 75 in each, right? 75 here and 75 right there. If the curve is approximately an arc of a circle. The race car is at 100 miles per hour right here and 250 miles per hour right here at point B, so it is increased by 150 miles per hour. It's being tracked by a radar unit, and that's positioned at the center of the track, and that radar unit uses polar coordinates. All right. Given the location of the radar as shown, determine the radial and angular, aka transverse, parameters, variables of interest. It will report when the car is at point B. Okay, so what we want to do first is try to figure out what its velocity and acceleration are going to be in different coordinate systems. It will really help us to use, and I can't recall how I did this right here, so I'm looking at this as I'm reading here, because I'm actually combining two examples together. It's actually example 4.2 and example 4.5. Excuse me, 4.2 and 5.2. Combined. So first off, I'm going to get the velocity at A into feet per second. So that's 100 times feet times 5,200 miles per hour. 100 miles per hour times 5,280 feet per mile divided by 3,600 seconds per hour, so we get 146.7 feet per second. VB is 250 miles per hour, and doing the same thing, we get it out to be 366.7 feet per second. It also occurs to me that I had messed up at some point, and this is like way too fast, and so like for reality. But anyway, I'm going to think about the arc that this thing makes right here, right? So the delta S, that was supposed to be a delta, looks like an upside down heart. The delta S that this thing makes is going to be the angle, or this, not the angle, but the radius times the change in angle right here, right? So that's going to be 300 feet, right? That was given in yards, and the angle is 150, but we need to turn that into radians. So multiply by pi and divide by 180, right? And if you do that, you're going to have 785.4 feet. In order to figure out what its tangential acceleration is going to be, we would take v squared equals v initial squared plus 2 times and this will be the tangential, that'll be the increase in speed right here. So we can say that it's doing it, we'll assume that it's doing it at a constant rate, and that's going to be times its delta S right there, right? So what we're finding is 366.7 squared is equal to 146.7 squared plus 2 times AT times our delta S, 785.4. Right? So we can find that our tangential acceleration is 71.89 feet per second squared. We'll find that our normal acceleration, right, because it's changing direction, is going to be v squared over rho, which the v squared at this location right here is 366.7 squared divided by our 300. So we get 448.2 feet per second squared. Now this is a ridiculously large number. Whoops, ridiculously large number, because if you divide it by 32.2, that's something obscene, like how many G's that's going to end up being, right? And then I think that would pretty much going to kill any human. 32.2, yeah, that's like almost 14 G's. That's like way crazy. But anyway, that's the this would be the acceleration that we would report in normal and tangential coordinates. So 71.9 ET. I should say 8.9. I should keep it. I'll just keep it as 8.9. 8.9. And then 448.2 EN, and that's feet per second squared. And the what we want to do, and also we could also say that the velocity, maybe I also want to put that there, at this time is 366.7 feet per, ET, right? And nothing in the normal direction, feet per second. Now, I'm trying to remember the process that I went through. Let me take a peek at the next chapter here, because I want to turn this into, okay. So I'm going to do 2 coordinate transformations as part of this. So there's exercise in coordinate transformations here. The coordinate transformation that we'll do here, I want to turn these both into x and y coordinates. So I have my I and my j right here, and at this location right here, my normal is going to be coming up in that direction, and my tangential is in that direction, right? So this is my EN and my ET, right? I drew it out of camera frame. I'm a little nervous because I have 28 minutes left and I didn't do the Kahoot thing I meant to do. I forgot all about this, but that's okay. We'll figure it out. And anyway, the angle that we're referring to, that 75 degrees, is what we had in the original one right there. So it would appear like right in there, and then it would also appear right in here. So if we're going to build a coordinate transformation array, if we have I and J and ET and EN right in there, we take the ET and we would see that we're going to have the sine of this angle, and it's going to be the negative of the cosine of that angle. And then for the EN right here, we could see that it would be the cosine of that angle, and then here it would be the and they're both positive. So and that angle is 75 degrees. So applying it to, let's see, I guess I applied it to both the velocity. Okay, so first I'll do the velocity. So the velocity, now written out, is going to be 366.7 right here. So that's only in the tangential, so it's going to be multiplied by sine 75 I plus, or I should say minus, really, minus. I can put it either way I want. Minus the cosine 75 J right there. And what we end up with is 354.2 I minus 94.91 J, and that's feet per second. if we take the acceleration now, that's going to be a little bit more because there's two parts to this thing. And let's see, how did I write that out? I said it was going to be, I wrote it out this way, kind of long ways. I take my 71.89 and I multiply it by the sine of 75, and then I take my, looking at this, I take my 4, so, and I'm adding 448.2, and that's the normal, and I multiply it by the cosine of 75. That's going to be I, and then I'm going to carry this down, and then I take the 71.89, multiply it by the cosine, so it's going to be a negative 71.89 cosine of 75, and then take my 448.2 and multiply it by the sine of 75. And I will get, let's see, double check I did that right. Yes, I will get an acceleration that looks like 185.4 I plus 414.4 J feet per second squared. Okay, so now I have them in rectangular coordinates, but I want to get them into polar coordinates. So that's like some of my motivation in doing it to rectangular coordinates. I'm kind of using that as the go-between. I could have transformed them directly from normal into polar, but I didn't have it written down that way. Let me pause the video just for a second, see where I'm at anyway. I'm at the 12-minute mark. Okay, carrying on. So now I have to figure out how to get these two into polar coordinates. Well, to start out with, let's go back to this original one up here, and we need to figure out, first off, where, okay, so this one's in the center. We need to figure out the orientation. We need to figure out r and theta. Well, now when we're dealing with polar coordinates, you should kind of like to organize your thoughts. Look for the variables of interest, right? And so that's going to be r theta, r dot, theta dot, r double dot, theta double dot. We're on a mission to try to find those. Now we might be given them. They might be we might need to take the derivatives of some functions to find them, but that's the basic approaches. We want to try to find those variables of interest. Drink a cup of coffee on the video. So in this dimension right here, let's see, you gotta try to remember. It's not written out that way. Okay. So first off, this r distance that I have right in here, I want to find r is going to be, so there's half the distance. There's 250 yards to right here, and these are 100 yards. But so like that would be down to there, but this distance isn't okay. Let's see if I'm going to say this correct right here. Yep. All right. so there's a little bit of geometry right in here, because this angle. Am I going to say that correctly? Let me double check. This angle is not going to be 75 degrees. We're going to have to find, yes. Yeah, I'm trying to think on the fly here. I'll write down what this is right here. We have, for our x distance, no, that's the y distance. The x distance is 1/2 of this, plus the cosine, of the 300 right here. So let me just write that down. All right, so 250 times 250 times 3, 750. 1/2 of that ends up being 375 feet right there, right? From here to here. But also, we want to take a look at, we have this distance. Okay, so we want this distance right there. Yeah, okay. So we have to add this distance right here to our 375, right? That's the horizontal. And this distance right here is 300. And this angle right here is 75 degrees, right? So for the x direction, we have 375 plus 300 times the cosine of our 75 degrees. Okay, yeah. And that's what I wrote down. And inside, before we square this, we're going to need this in a second. We have 452.7. That's inside the square root. And then this vertical one right here is going to be just 300 right here, because that's this times the sine of 75. Yeah. And that's squared. And I'm going to get what that thing is inside there too, is 289.8. So what we end up with in terms of this length is 537.5 feet. And then the angle, and we want to try to get the angle as reported, I believe, is going to be this angle right there. So that's the one that we're going to call theta. It's going to be the same angle as that one right there, right? So that's how we're going to report it. So we'll take the inverse tan of our 289.8 over 452.7, and we're left with 32.63 degrees. So we got 2 of our variables of interest so far. Now the remainder ones we need to do by getting doing a coordinate transformation and getting it into polar coordinates. So that's going to require us to, once again, superimpose on an I and a j, because we have them in terms of I and j right now. We could have gone the other way, but we didn't. And our polar is going to be aligned, our radial is going to be aligned with this, and our, by convention, our transverse is going to be right-hand rule, thumb over that way, right there. It's going to be pointing to the left by convention. I think that's true. Is that true? I don't like this. I guess because I'm going counterclockwise. Yes, that's true. Yep, counterclockwise. So that makes that true. All right, I just wanted to double check. And I want to draw this angle kind of correctly here. So it's kind of that way right here, right? So this is the angle, what we're calling theta. And I guess that would be over here too, right? So right here is radial, excuse me. It's all polar. And here is the transverse right in there. So if we're doing a coordinate transformation array, let's say I, J, E, R, E, theta. How am I doing on time? I got 15 minutes to close. ER should be cosine, negative cosine, right? For I, because it's in the negative I direction. So negative cosine of theta. And then J is going to be negative sine of theta, because it's going downwards, and it's of J, and it's opposite. Over here, we could, this is going to be the positive sine of theta, and then this is the negative cosine of theta. So we apply those to what we found over here. And so for the, I guess I'll do it over here to the decide for the velocity what we want to do. And by the way, that theta, we want to make sure that theta is now 32.63. So let's put this up here. 32.63, and transforming it. Yes. Okay, we take 354.2 and multiply it by, we're going down this way, right there, right? So we have multiplied by the cosine of 32.63 ER, right? Plus the sine of 32.63 E theta, right? And that's going to be plus, and then we go over to here, and we're going to have a minus 94.91 times the sine of 32.63 ER, and plus, or I should say minus, maybe. Just put a minus in there, right? Did I do this right? This should have been minus. And this should be minus right there. Minus, minus. Cosine of 32.63 E theta. Right? So if we get a velocity right here, now in these coordinates is going to be negative 247.1 ER plus 270.9 E theta feet per second. In a similar manner, we need to now take acceleration and turn this acceleration right here into polar coordinates. So this acceleration, and I wrote this out slightly differently there. Okay, I said that I'm going to take 185.4, multiply it by my negative cosine of, what's the angle again? I said 32.63. 32.63, could have looked over there, right? ER, and then I'm taking that and multiplying down there, so I get a plus sine of 32.63 E theta, and then take this right here, our 414.4, and multiply it by this column right there, minus sine 32.63 ER, and then minus cosine of 32.63 E theta feet per second squared. So once we have that, we can find that the acceleration now, rewriting the thing out, is going to be negative 378.6 ER and negative 249 E theta feet per second squared. Okay. So we have these two things, and we've transformed them. Now we want to turn them into polar coordinates. Well, what we could find first off is this right here is going to be VR, and this is V theta. So VR is R dot, which means that's equal to 247.1 feet per second. So that's one of our variables of interest. V theta is going to be R theta dot, and we know that that's equal to 270.9 feet per I'm getting distracted by my alerts that class starts in 10 minutes. Feet per second. And but we also know that's going to be equal to r, which we found was 537.5 right up here, right? Theta dot. So theta dot is just equal to 270.9 divided by 537.5, right? And we find that a theta dot is therefore 0.5040 radians per second. Did that come off the edge of the paper? No, it didn't. I went down there. Okay, sorry. So we have r dot and we have theta dot. So we have r, we found r, found theta, we found r dot, and then now we have theta dot. Now we go and we find this guy is going to be our AR, whereas this is A theta. So let's find, let's use this AR is negative 378.6, but we know that's equal to our double dot minus our theta dot squared. But we know that that we have our double dot, we have minus, we have the r already, 537.5, and we just got theta dot, so it's 0.5040 squared. From that, we're able to get r double dot. So we get r double dot is negative 243.1 feet per second squared. And then lastly, we take this A theta, which we happen to know is negative 249.0, and that's going to be r theta double dot plus 2 r dot theta dot. Well, we know this r dot we just found, we know theta dot we just found. So that's going to be r, which is 537.5 times theta double dot plus 2 r dot, which we found up here, which is negative 247.1 times theta dot, which we found to be positive, by the way. That means that it is counterclockwise. Right there. And so we can find theta double dot, which we find to be a very small number, 3.289 e to the minus 4 feet per second squared. So the answers, the variables of interest, we have r is equal to 538 feet, theta is equal to 32.6 degrees, which is going to be measured that way. R dot is negative 274 feet per second. Theta dot is, we should write this out as a clockwise, but we'll just go ahead and keep it as a positive means, counterclockwise. R double dot, I'm looking at the time, we got 5 minutes, 6 minutes of the class. R double dot is a negative 243 feet per second squared, and a theta double dot is the very small 3.29 e minus 4 radians per second squared. So, thinking about what this means in terms of this would be what the radar dish, and the radar dish isn't necessarily pointing towards the thing, but that's okay. It's measuring that this arc is changing at this speed. Here's the range. These are all the things that, from this type of perspective, these are the parameters it would be considering to understand what the motion was of the car. So that's a longish video, but it was a longish example, and it's a half hour long. Let's see how it goes in class. Thank you.